throughout history, religious narratives have provided explanations for the origins of life, the universe, and humanity, Hess' place within it. Sacred texts such as the Book of Genesis describe a divine creation, where the world and all living beings were formed by an omnipotent deity in a structured and intentional manner. These religious accounts have shaped cultures, moral frameworks, and human understanding for millennia. However, as scientific inquiry has advanced, discoveries in fields such as cosmology, biology, and geology have presented alternative explanations that often contradict traditional religious teachings. The Big Bang Theory challenges the notion of a static God-created universe. Lequas later in the series cover more of these examples. We will explore key scientific discoveries that have challenged religious beliefs, highlighting the ongoing dialogue between faith and reason, tradition and empirical evidence. While some view these scientific advancements as threats to religious doctrines, others see them as opportunities to deepen their understanding of spirituality in a world illuminated by science. In the end, you will have to come to a conclusion yourself. First, we will discuss just what science has to say about the Big Bang, Genesis, and the Kalam cosmological arguments sometimes argued for a creator, uncovering what modern science has to say in response.
If we're thinking about philosophy of science, what do you think would be an important aspect of, say, cosmological science, like how the universe first came to exist, and those type of questions? Can we bring philosophy of science into kind of figuring out those type of big questions?
Yes and no. For example, right now I'm teaching a cosmology course. And it's kind of interesting. I'm not a cosmologist, so I kind of do it essentially as a kind of a philosophy of science course in some ways, because these are advanced students, and up to then, they've probably learned a lot of physics, as in, this is in the textbooks. This really works very well. But there's a big difference between the physics of, say, transistors, of what works in your cell phones and things like that, and the physics that goes in cosmology. Cosmology is much younger, much more uncertain, much less constrained by data. And so therefore, cosmology is actually a good place to explore how science works when it's more at the cutting edge and more when you're dealing with uncertainty all the time. Mm-hmm. And so you might have a temptation to say that philosophers of science will usually start by laying down, here are some good examples of scientific reasoning. Here are some common characteristics of how you're supposed to reason when you're doing science and everything like that. Curiously enough, once you come to cosmology, we probably throw all of that out the window. I mean, just about anything in the Schick and Von textbook that you'd use as a sort of an example of a rule of science, in cosmology, at some point, we sort of start at least skirting around it at some point. It's full of things where we don't exactly know what we're doing. We can't confidently say that we're replacing one unknown with another. We have all of these adjustable parameters and everything like that. So you get a sort of a feel in cosmology that a lot of what you're doing is making it up as you go along, trying the best that you can in very imperfect conditions. And sometimes that needs a bit of emphasis in science too, in a sense that science is sometimes a good tool of managing uncertainty and doing an imperfect job with whatever imperfect information that you have. It doesn't always fit a textbook pattern. So sometimes cosmology is a good example because of that.
Well, I'm not sure what you mean by alternatives to the Big Bang. So there are models. Again, it depends on what we mean by the Big Bang. The Big Bang is sort of a theoretical framework for understanding space, time, and matter that's anchored to the idea that space is expanding. All the evidence points in that direction. So whatever alternatives we imagine, to exist, they have to be compatible with that data. So there are models that say that the time of the Big Bang is not the beginning of time. They address all the same observations, um, but they have a view of time that is different, that involves cycles of time. Um, and then there are so the answer is yes, that there are different models that are all compatible with the data.
I don't believe in the Big Bang because there has been a theory rather well worked out of how the Big Bang is supposed to have happened. And it seems to me that it is not likely to be correct. So there are too many assumptions in it for me to like it, and it is too far removed from astronomical observation. Quite obviously, we can't observe what happened 10,000 million years ago, whereas we can observe what happens in the center of a galaxy today. And so I prefer always to choose the alternative that allows one to carry out observations now. I don't like the idea that something is dependent on a cause that I can never verify. So I don't like this because it's in the past. It's all over and done with. I can't get at it, as it were. So I tend to avoid it. I don't like it.
The steady state model. That was. I mean, that had something attractive about it in the sense that it seemed a little bit more compatible with the laws of nature. But it wasn't compatible with the observational data, in particular the cosmic microwave background. And so, yes, so that was discarded. But that doesn't mean that we can't still imagine models that have time that doesn't have a beginning, that goes on to infinity in both the past and the future. And again, there's something attractive about those kinds of models, given the laws of nature.
1950s, he believed in the steady state model and that some of the parameters we measure were fake. And he's sort of in the minority. The fact that the universe is infinitely old and static, and you have to explain away a lot of Big Bang evidence to sort of have that theory, but that's called the steady state theory. And that's really the only alternative I know of to the Big Bang.
Foundational pieces of evidence for the Big Bang cosmology.
Yes.
So could you talk a little bit about that?
Yeah, so the idea is that the universe, this is what's always confusing. It's not really expanding into anything. The whole universe is just expanding. And maybe after about 400,000 years, it started to cool. For the first, few 100,000 years, it's too hot for atoms to even form. So you have, electrons and protons not combining. And so then at some point, the universe cooled enough to be transparent to radiation. And then you can think of it as being stretched, like you're stretching a balloon. And so that 3,000 degree gas from 13.3 billion years ago is now cooled down to about 3 degrees Kelvin. And what was his name at Princeton? I forgot his name. Yes. Robert Dickey at Princeton was working on this idea that you should be able to detect this. And Penzias and Wilson were at AT&T Bell Labs, and they were trying to do some other observations of supernova remnants. And they kept seeing all this static no matter where they pointed their horn antenna. And Penz, they got the Nobel Prize for the cosmic microwave background in 1978. And Penzias just passed away about 2 weeks ago. I think he was 90 or so. But they made this serendipitous discovery. You know, the antenna was full of pigeon crap, so they had it cleaned, thinking it would get rid of the noise. And after that, it still had all this static, and anywhere they looked. And so and talking to the people at Princeton, they realized, hey, we've discovered this prediction about the Big Bang, that there should be this leftover afterglow. And they measured about 3.5 Kelvin. Subsequent measurements got it down to about 2.7, which agrees with the expanding and cooling in the Big Bang. And of course, the clumpiness of the cosmic microwave background might tell you something about how galaxies formed. If there's big spots in the cosmic microwave background, like big clumps, it might indicate that there was lots of mass in the early universe making big galaxies or big structures. And if it's not so clumpy, then maybe the universe is empty. And until we discovered dark energy in the late 90s, we sort of thought the universe was mostly empty. It was only 20%, or now it's 4% real matter, 26% dark matter, and 70% dark energy, which doesn't give you a warm fuzzy feeling. But the cosmic microwave background, not only can you sort of say this is a good piece for the Big Bang, you can try to measure its clumpiness. And they do, I can have a slide later, but they try to do these autocorrelation functions to look at the structure. And now it looks like the universe wasn't really super clumpy and it wasn't super empty. It was kind of in between. And so this supports kind of a universe that will expand forever, just like a rocket that just has enough energy to leave the Earth. One that it's too slow to fall back. I mean, if the universe were super massive, it might have stopped expanding and collapsed, and then we wouldn't be here, right? So it had to just exactly have enough energy to sort of keep expanding, and it may expand forever. It may not. We'll talk about that later. But the fate of the universe is a fun topic. So.
So I would say the Big Bang didn't create anything. The Big Bang isn't a cause and effect kind of thing. I guess it kind of depends on what we mean by the Big Bang. If we mean the general theory, then this is a framework for understanding space-time, matter, and energy that simply cannot be extended beyond some point in time, which allows that point in time to be the beginning of time or not. And so those options are both open. And so, yeah, that's my answer to that. If you have a follow-up, we can go deeper, but
Yeah.
so in other words, I think it's a misconception to think of the Big Bang as a cause and effect kind of thing. Creation would be a cause and effect kind of thing.
A lot of people, the most common misconception I would say is, even if they know about the Big Bang, they have misconceptions about it. They think it was an explosion. They think that it was the very beginning of everything, including the birth of space and time. And they think that the Big Bang is also very much in doubt. That the Big Bang is just our leading theory now, but maybe someday we won't believe the Big Bang at all. And I don't think any of those things are true. The Big Bang is an idea that can trace its origins back to the 1920s, or in some cases, if you argue it, I don't believe those people. Some people say De Sitter in 1917. I don't think so. But the 1920s, that's 100 years ago. Mm-hmm. People were resistant to these ideas. People were skeptical. People threw every alternative they could at them. The thing is, there are 4 cornerstones of observations now that indicate that our universe, the way it is today, wasn't always like this. that it only became the way it is today because it has expanded and gravitated over billions of years of cosmic time, and that in the past the universe was smaller and denser and hotter and more uniform. And as you extrapolate back and back and back, you can come to this early time where things were very hot and very dense and very uniform. And all of what we have today arose from that early state. That's all the Big Bang is. That's why sometimes instead of the Big Bang, I call it the hot Big Bang, so that people don't get wedded to that old, outdated idea of, oh, singularity, birth of space and time. Yeah, I'm 1927. Like, no, come on, come further than that too. But the Big Bang has 4 cornerstones. One is this large-scale cosmic web that we've illustrated. Theory predicts it, simulations predict it, and we observe it. We observe how the universe grows up. This is one of the huge lessons that Hubble taught us and that the James Webb Space Telescope is teaching us. Number 2 is the fact that, oh, well, if you go back and back and back, you can see the universe as it was in the past. And we can see it was hotter in the past. It was denser in the past. Galaxies were smaller and less evolved in the past, and they've evolved and are more massive now, right? All of these things of evolution we see indicates the universe has expanded and is still expanding. We have a wide variety of measurements that support that. We also say, look, I can extrapolate, okay, the universe is like this now, but if I come back and back and back, it was smaller. And because light has a specific wavelength, and the wavelength of that light determines its energy, if the universe was smaller in the past and smaller in the past, then that wavelength of light was shorter in the past, which means higher energy, which means hotter. So at some point you can imagine, whoa, it was too hot to form neutral atoms. All you had was an ionized plasma. Well, what happens when plasmas become neutral? All the light that was bouncing off the ionized electrons now free streams throughout the universe, just streams unimpeded. We see that leftover light. We detected it back in the 1960s, and it's still there in all directions. That's what we call the cosmic microwave background. I like the older name for it when we called it the primeval fireball. Boom.
I love that.
Ooh, that's an
Better
awesome
name.
name.
I know. Look at us. We used to name things like electron after their amber color, and now we name things like gluon because it's like sticky and stuff.
Yeah.
Like we got a lot less poetic as time went on.
Yeah.
But primeval fireball, we see that. And the 4th cornerstone is, you can imagine going even hotter than that, to when we couldn't even make protons and neutrons bind together. Well, we see the light elements from when you finally could bind them together. Hydrogen, its isotope deuterium, helium-3, helium-4, isotopes of lithium. We can detect those from pristine samples of gas that have never formed stars before. And we see, yeah, they had none of the heavy elements that you only make inside stars. So all of those 4 together, the large-scale structure of the universe, the expansion of the universe, oh, that's a very sweet compliment. I promise you, I will not be the next Carl Sagan. I will be the first Ethan Siegel. And history will have to tell what that looks like. But I don't want to be anyone else. I only want to be myself. And I wish that for all of you out there. Don't try to be the next version of someone else. Be the best version of yourself.
That's awesome.
Absolutely.
The 3rd one is the cosmic microwave background. The 4th is the abundance of the light elements. No other theory explains all 4 of those. If you can come up with an alternative that explains those 4, you've got a real alternative to the Big Bang. People claim they do all the time, and when we look at them in detail, we say, nope, your spectrum for your CMB is not black body, get out of here. Nope, you make too much carbon, we don't have carbon, get out of here. No, your universe doesn't follow the expansion rate we've observed, get out of here, right? There's always a reason that if you look at it in detail, it falls apart. So that's what you have to do. You want to make an alternative theory, you better not let the current theory beat you. You got to go and beat it on its own turf.
Yes. So when you say Big Bang Theory, what you're referring to is the collection of physical laws that we've identified, but those physical laws we can't trace them back to this time, the t equals 0 time, if you will, of the Big Bang. So the math breaks down, and the question is, what happens at this time? We don't know, because we just don't have the math to deal with this. But what we do know is that there's been expansion, and we can trace this back, and all sorts of other physics comes together, and we can make sense of all sorts of observations. How hot it was, how dense it was, and how much stuff was made, because we have the equations of what's going on in stars and how elements are made, and so you can make predictions. And so you have a pretty good picture of what happens after t equals 0, but not at t equals 0. So what do? You can't conclude anything. So, Cease did a show on this. T equals 0 could be the beginning, but it doesn't have to be. We're not there yet. I'm glad to see that there are religious people who are happy with the Big Bang, because I've in the last few decades, there's been a lot of resistance to the Big Bang Theory based on religious grounds. But it seems to me that it's something that religious people should be excited about, right?
The Big Bang Theory and subsequent astronomical research provide a naturalistic account of the universe's origins, contrasting with religious creation stories found in texts like Genesis. Let us first hear what scientists and philosophers have to say about the Big Bang and the KKA and other narratives versus what we know from science. Developments in cosmology, including the Big Bang Theory, offer an account of the origin of the universe based on observational evidence. This scientific framework challenges certain traditional narratives about creation found in some religious teachings.
Being knows this is where we came from. We long to return. And we can, because the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself.
If we are not able to ask skeptical questions, to interrogate those who tell us that something is true, to be skeptical of those in authority, then we're up for grabs for the next charlatan, political or religious, who comes ambling along.